What's the point?
We want to hear.
Can anybody provide the sound?
So we'll hear this at 3 o'clock, of course. There's somebody from the academy. Okay? Thank you.
Let me get back to
Yeah, so I was talking about how smaller active regions would be expected to have larger helicities and larger active regions would be expected to have smaller helicities. Now, in the next part of the work, we use a flux transport dynamo model with a Babcock Clayton alpha effect to calculate the helicities generated by this mechanism in the model. So now in our model, which is incidentally called Surya, which is the Sanskrit word for the sun. We have this buoyancy algorithm which does the following. A flux eruption takes place in the model whenever the toroidal field at the bottom of the convection zone exceeds a critical value. Now when such an eruption happens, we calculate the poloidal flux phi in the convection zone, which is supposed to be dragged by the rising flux tube. Using this equation,
Why this company? Why you choose this company, not five companies?
phi component. Which phi component?
Mm.
Oh, because that is the toroidal field, and we are talking about the toroidal field is, if it's in terms of the flux tubes, then the toroidal field is dragging this poloidal flux, which is weak, and it's all over the convection zone. So we calculate this flux using this integral over d theta over dr, where dr goes from the bottom of the convection, r goes from the bottom of the convection zone to the top. And then we compare the sign of this flux and the erupted field, Bz, which is the B phi or the B. And whenever this flux and the toroidal field have the same signs, we say that the erupted field has helicity, which is negative. And when this flux and the toroidal field have opposite signs, then the helicity acquired is positive. Now using this sign convention, we can have the butterfly diagram of helicity from our model. So these are the latitudes at which there have been sunspot eruptions in the model. And the red color, and the plus signs actually denote positive toroidal field, and the circles are negative toroidal field in the north and the south. And the red color is the positive helicity, and the black one is the negative helicity. So we find that at the beginning of the solar cycle, the helicity in the northern hemisphere should be positive, and which means that it doesn't obey the hemispheric helicity rule, which is actually a very weak rule at the beginning of the cycle, whereas as you proceed towards the cycle maxima, predominantly negative helicity active regions appear on the northern hemisphere, and positive helicity active regions appear in the southern hemisphere. So now here I have just plotted the vertical axis is the magnitude of the alpha, and this is the latitude for various phases of the cycle. So the upper plot is for all the eruptions in the entire cycle. So they are just distributed like that. And here I have just taken the 4 years, from 4 years around the maximum of the solar cycle. And here also I get that the sunspots in the northern hemisphere are negative helicity, and those in the south have positive helicity. Whereas if I count only the sunspots during first 4 years at the beginning of the solar cycle, the trend of helicity is opposite to the hemispheric rule in our model. And one thing is that this is a very regular model. We haven't introduced any stochastic fluctuations in the model. Now, since this is a Babcock-Leighton alpha effect, and Sasha was showing this figure about the Joyce law, and you might have observed that there is a huge scatter about the Joyce law, and that would introduce a lot of fluctuations in the generation of the toroidal field at the surface, and that would probably give rise to a more sandpaper-like appearance in the helicity butterfly diagram. So here what we have done is we have just plotted d alpha by d lambda is the latitude or whatever, and in this axis, and this is the time in units of the dynamo period. So this is the phase of the dynamo cycle. and we have divided the dynamo cycle into 2-year bins, and for each of those 2 years you have calculated the slope of the alpha by just fitting a least square fit to the number of active regions in the north and the south. And we find that this d alpha by d lambda would probably have a dependence like this. So we see that for most part of the cycle, the d alpha by d lambda is actually negative, which means the northern hemisphere again has negative helicity, and for a small part of the cycle, which appears at the beginning, it has positive helicity. So now there can be different sources of error on this estimation of helicity. One is that we have assumed that the colloidal field lines, in the back of the envelope calculation that I showed, we have assumed that the colloidal field lines, they get diffused in the entire flux tube, in the cross section of the entire flux tube, whereas that may not be the case. The helicity might just appear in a narrow sheath of width which is much less than the radius of the flux tube. And moreover, when you look at the helicities in the chromosphere or in the corona, when Parker had proposed long back that a twist of an omega loop accumulates at the inflated apex, thereby decreasing the twist of the active regions. So I mean, there can be there can be many sources of errors, but I have just shown 2 of them. So I don't have much time, right? No?
Yeah, 7 minutes or something.
7 minutes, okay. So after I talked about the distribution of helicity from active regions, so then we, after I talked about the butterfly diagram of helicity, now I go over to talking about distribution of helicity in an active region. So this is a simple 1D model where we solve for Bz, which is the toroidal field, and B5, which is the colloidal field. And this model includes accretion of B5 by the rising flux tube. We have done this calculation in the Lagrangian frame of the expanding tube. So actually we have made very bold assumptions. For example, like the flux tube expands, as the flux tube rises from the bottom of the convection zone to the surface, it expands, and it expands in a self-similar fashion. So now instead of working in an Eulerian frame, we can go to a Lagrangian frame where the flux tube radius psi is constant in absence of any diffusivity. And then we also have to use a thin flux tube equation, which would give us the rate of accretion of the colloidal field by the rising flux tube. So this is with the basic geometry of what I am talking about. So this is the flux tube, which has a field like that going perpendicular to the plane of the paper, and these are the colloidal field lines. And as the flux tube rises with a particular velocity, you will have a flow which looks like a flow around a cylinder, and these colloidal field lines would get wrapped around this flux tube, and this would continue as it rises. So these are the equations. So this is something I would need to talk about. We have introduced a nonlinear turbulent diffusivity in this model, which means that this part is actually a Kolmogorov-like dependence on the size of the turbulent eddies. So and h is the pressure scale height. So whenever the tube radius is much smaller than the pressure scale height, the turbulence doesn't destroy the flux tube. It probably just moves it around. Whereas as the flux tube expands, more and more turbulent eddies accumulate in its cross section, and when that happens, the diffusivity increases. So it is that effect. And we have also included a simple algebraic quenching. This is the equipartition magnetic field, and the equipartition magnetic field was calculated by a model by Uno and Uno, I suppose. Yeah. So this is the nonlinear diffusion equation, and this model actually was developed.
Excuse me, your last remark, turbulent diffusivity, in this paper the kappa was 7, wasn't it?
What?
In this paper, Petrovai and
Yes,
Moreno,
yes,
etc.,
yes,
the
yes.
kappa was 7. Not
Kappa, I think we have done, I think they also probably varied their kappa for different.
Not 2.
Yeah, but maybe, I don't think it was as large as 7. I look it up. I looked that up. But essentially what they, this paper was essentially looking into the decay rate of sunspots. So they had a model of turbulent erosion of flux tubes, where the turbulence is eating or gnawing at the periphery of the flux tube, and the sunspot is decaying. And their claim was that this model matches the flux tube, matches the sunspot decay law very well.
Yeah, but
So-
with kappa 7 and not 2.
Okay, I'll verify that claim definitely. So, but then we have used a factor of 2 because that sounded like reasonable. I mean, not so large. I mean, we have done some calculations with kappa is equal to 5, and
Maybe.
but I mean, for most of the simulations we have kappa is equal to 2. So we have basically have 2 different cases. One where we allow the magnetic field to expand like it wants to. Then what happens when it rises to the surface, the flux, there is so much of flux loss in the flux tube, the magnetic field is so weak that, I mean, it is difficult to believe that that will form any kind of sunspot. For example, that such a flux tube would probably end up having a field of 300 Gauss or something. So what we have done is, now since sunspots are observed to have magnetic fields which are 3 times the equipartition magnetic field at the surface. So what we have done is that after the magnetic field in the flux tube reaches that value of equipartition field, we artificially do not allow the magnetic field in the flux tube to decrease below 3 times the equipartition, or I mean, we have done 2 different calculations. One is that we restrict the flux tube magnetic field to be greater than 3 times the equipartition, and here we restrict it up to the equipartition field. So this is the case A where we didn't have any restrictions. So as I said, at the end we found that the flux tube magnetic field had become very weak, and the helicity, you cannot see, but I can just tell you that the helicity is actually very weak. So, and it's smeared across the cross section of the flux tube in this case. Whereas in the case B, where we restricted the magnetic field in the tube to be greater than 3 times the equipartition, the magnetic field obviously retains reasonable values, and the twist has a distribution like this, and the prediction is that the sunspot should have a region of opposite helicity in a narrow region outside at the periphery of the sunspot. So for example, in the northern hemisphere, if the sunspot has negative helicity at the center, it should have a region of positive helicity at the periphery. And now I think there are some high resolution observations from Hinode, but they don't have data for many sunspots, so till now it is not possible to throw light on whether this theory really is valid or just nonsense. So now we calculate the flux in the tube using just this equation, and we see that the flux loss from the tube is around 45% for the case B3, where we restricted the magnetic field in the flux tube to be 3 times the equipartition. And in contrast to the cases A, where there were about 90% of flux which was lost from the tube and nothing was left in the tube reached the surface. And the reason, and the probable reason why the flux tube should be concentrated the field in the flux tube should be concentrated to values above the equipartition field. Are these a phenomena of convective collapse and turbulent pumping, or which might try to concentrate the magnetic field in the flux tube? So with this, I'll just go over to the conclusions. So there are two different predictions. One is that smaller active regions should have statistically stronger helicity. And at the beginning of the solar cycle, the helicity should be opposite of the usual trend, which Kirill says that he observes in his data. And addition of stochastic fluctuations to the Babcock Latent alpha can lead to a more saltpaper appearance in the helicity butterfly diagram. And then the contribution of the colloidal field accretion to the twist can be quite significant. And the last result is that this gives rise to a ring of reverse current helicity on the periphery of the active region. However, the resulting twist depends sensitively on the structure of the magnetic field in the subsurface. So, since we don't have any information about this, about the subsurface phenomena, so it is difficult to say, what is really happening there. And but I would like to say that the sigma effect, which was proposed by Longthorpe et al., can be an equal contributor to the helicity of the active regions compared to other dynamo-generated methods.
Okay, thank you, Kiani. We have time for some short questions.
What's the contrast between density and the models?
You mean the flux tube? Oh, we have taken this density from convection zone model.
So, real.
Yeah, it's real.
It's a gradient, it's not homogeneous.
Huh?
It's a profile, a density
It's
profile.
yeah, it's a profile, yeah.
And do you need rotation for your
We haven't included rotation here. This is a simple 1D model. So, are you talking about the dynamo model or the...
No, the helicity, current helicity, after my feeling, current helicity can only exist if the system rotates, like the kinetic helicity, like the
yes.
alpha effect. I'm surprised. You have no rotation?
No, for example, in the dynamo model, we put in the Babcock-Latent alpha by hand, but then the Babcock-Latent alpha is the effect of the Coriolis, supposed to be the effect of the Coriolis force. That is again because of rotation.
Or this one.
Yeah, the d phi, but nevertheless, the computation of the helicity is not. I expect it's zero. If
No,
it
so his question is really what happened if
Is the
the
switch
sun
off
were
of
to
the
rotate the
computer?
other way around? And then you would be saying that your Babcock-Latent mechanism would also twist then the regions would be opposite twist, right? J's choice all would be different. And would then your helicity change?
Yes, of course. Then I would probably take alpha effect to be negative in the northern hemisphere,
right.
and the Babcock-Latent alpha to be negative in the northern hemisphere. And
So this in principle should answer your question.
how?
Because the Babcock-Latent mechanism changes sign, and that changes helicity.
And okay, if you're talking about
Yeah, but the
1D
sign
model,
of the b phi is not important. This was the yesterday discussion. I do not believe that the sign of the phi is important.
Of course it's not important.
sign of what?
Sign of b phi is not important. Of course not. It's a quadratic quantity, right?
B phi is a quadrant. No, but when you calculate alpha, it is j by b phi. So there, the sign of b phi is obviously important.
And then j would change.
Yeah, but once you invert b5, you invert j. No?
Okay.
Maybe we can continue this discussion later and go on to our next speaker.
Sorry. This what? It's the same one. Oh, you with the same thing? Yeah. After the ship. And we don't have it here?
Yes, the first, yeah, this, no, this, the second, yes, this one.
So maybe if I have it already here?
Yeah.
No,
Mhm.
Is it now? Because it's bigger, right? Is that one? Is this one?
The one, no, yes, this one. Yes, so I have to. Yeah. I have to.
Film?
You want to-
We go.
Okay. No, this is the first one.
No, und?
Okay, the next talk will be from Luis Garcia, deandrade. Yeah, from Sao Paulo,
No, from Rio.
from Rio,
Yeah.
sorry.
Olympic.
No,
And we will
He's from
speak about
Korea.
COVID. He will speak about curvature stretching,
Yeah.
anti-correlation in solar bands.
Yeah, okay. Thank you. This is basically the idea of, oh, that's it. That was the first. I'm following the ideas of chatterjee and Cowley and collaborators on the anti-correlation between curvature and stretching. In magnetic fields, of course, in turbulent filamentary dynamos, and applying this idea to flux tubes. And of course, this is the advantage is that this is no numerical stuff. I'm trying to save time here. This is justification why I use the flux tubes. And let's see if I have it today. I'm trying to. This is what the model is based in. Okay, this is the first part that is important. I used to build this model. I used the coordinate that was done by Renzo Rica, and he used very simple evolution equations, which is the Frenet equation, vector equation for the tube, and the twisted of the tube is already in the coordinate system. And yes, we have to go there and go back. Yeah, okay. Yeah.
Can maybe even this is the word.
That's not that good. You have a point. Oh, that's
That's what.
Yours?
Yeah.
I can see.
I mean yours. It was
No, okay, no. This is not a point.
No, but this is a stereo. It doesn't work.
Yeah, I mean, change it. I want to point.
Das?
Yeah, okay, yes. Oh, okay. I get closer, okay, I understand. Okay, this idea of this stretching twist and fold system is present in some experiments. This is an experiment that was performed for the first time by Chris Forrester and his Wisconsin group. And and this appears, of course, in the tubes as well. Okay, this the real solar pictures and the diagrams here. That's after the cleaning picture. And from here you see that the tube is twisting and stretching because the size of the tube is growing, of course. So you have stretching here, and you have you may have folding there. Folding here for me is also curvature. The piston tubes. Okay, I'm not considering me for that. No, that's the model. The metric is 14 tubes. I mean, you have no any other metric coefficient here. In general, when the tubes are thick, you have this this term multiplied by the axis of symmetry, the magnetic field. And but I just considered the case where k is equal to 1 to get the solution, analytical solution. Okay. Here's what I mentioned before, the twist, this torsion tensor, torsion scalar, and this is the twist angle. Well, uniform stressing has been considered by all these people here, as I mentioned in the other seminar. And also remaining dynamos of a negative curvature has been considered by these two people as well. Okay. And that's more of announcement of results, the previous results. Jean-Luc Tifo, this American mathematician, has worked out before chatterjee. He has worked out in chaotic flows where this turbulence, this relation, this anti-correlation appears between stretching and curvature. What I mean by that, of course, is when your stretching grows, of course your dynamo action grows and your curvature decreases. Okay, here's some geometry too of the tube. This is Riemann curvature. This K is Gaussian curvature, and G is the determinant of measure. This is the way I can introduce I will introduce this in the dynamo equation. Okay, and that's the equation. That's familiar from kinematic dynamos. Okay, I'm considering a very simple model. You can see the radial of the magnetic field here is considered to be 0. So it's a very rudimentary sample. And here I compute term by term of this equation, here spanning. The first term is the stretching term, of course. And you can see from here, this is analytical simple computation, that this, sorry, okay.
ST, T is not time.
Sorry?
In second line, T is not time. It is
Here?
No, in second line. Second line.
No. This is vector.
This way.
This vector is
Unit
actually
vector.
tangent. Yes, tangent to this tube axis here. Okay, to the flux tube axis. Okay, and as I was saying, you can see here that the stretching term of the is actually anti-correlated with the remaining curvature of the tube. And this is what is concerned with chatterjee idea of the stretch and shear relation of the magnetic fields. And here's a nice example to that this can be done without frame wave. Yeah, it's not working anymore. Oh, sorry. Okay, that is, I extract this from the chatterjee+garcia's paper in Calvin. And as you can see from here, this is a turbulent magnetic field. This is stretching, and this is curvature. So you have a good idea that the places where curvature is decreasing, the magnetic field is increasing. Okay, so they are really anti-correlated. Okay, that's I tried to test the model. I used some strong constraint on the frequencies, which I call the resonance between the poloidal frequency and the toroidal frequency. I mean that they coincide by force. And I also compute the kinetic elasticity here, which has this interesting property to be really not anti-correlated, but correlated to the remaining curvatures. I mean, as the curvature increases, the elasticity increases as well. Is that okay? You don't believe that?
I believe, but it's natural.
But is it okay? Yeah, it's natural. Well, the idea of the model was to use a more geometrical frame into the model and to check what this gives to the non-data in the solar physics and plasma laboratory. So they will become soon. So the stretching term is what's already computed, and then I pass to the diffusion term. So I compute also the diffusion term. As you can see, it's really very strongly anti-correlated with the curvature. So because now the exponent is -2, so it's non-linearly correlated, anti-correlated. Okay, and
It's square.
sorry,
Because it's that square, right? Because it's that square.
Yeah.
Over.
non-linear in this sense. Okay. Yeah, okay. And well, here there are some numbers. If you consider the solar data and compute the curvature from this data, you would see for this kind of relation that you compute the poloidal field amplification. And besides that, what I found interesting, here there is, there is some relation, for those of you that attend the first MRI gave, to the negative curvature problem. You see from here, you can see this is the lambda is the magnetic field amplification rate, okay, and this is curvature, okay. So you see from here, since this term is negative, this is frequency, this is scalar curvature, which is also positive. So you can see from here that only in the case that K is negative, you have dynamo action. And this is the same result actually was shown by Shikoni and Latushkin in 1997, but which Dmitry mentioned last Friday, I guess. And in this limit, then you have this result. So, yeah, this is inflectionary points. I'll get there. What's the inflectionary point is in the solar. That's the idea. This is Renzo pictures. Actually, these are the inflectionary points. I mean, if you can see this, these are saddle points. So the Riemannian curvature is negative over here in this points, on those points. Okay, and this it could be an example of where the dynamo action is, and especially the question I put to Peter is that if this is not static, of course, and when this you may shift the negative curvature to positive curvature. And simply doing more stuff like that. from here to here. By the way, so he would change the nature of the curvature. Okay. So, and the point is that if you twist, this is a twist factor, and if you increase your twisting, you know, you would end up with breaking the tubes.
So what
That kind of corrosion.
So
Cement.
I still didn't know what this omega was. And when you change this kind of
This-
twist, you said there is no dynamo. And then
No.
Nathan was saying yes. Can you explain this maybe?
I think it's something local. What I understand from this talk, if you've got some local configuration, you've got some kind of motion, a photo turbulence, and you've got a negative curvature in some place, you can, how to say, change nature of diffusion mode to some kind of dynamo, diffusion dynamo, if you like. Yeah, there's something in this space.
I thought it's a tube.
Yeah, it's
right?
tube, of course, it's tube.
So what is
It's
a tube with negative curvature?
Sorry?
A tube with negative curvature?
No, it's actually actually considered locally, as I said, in some points. I mean, let me
That's what
let me draw here. I think it's better.
I mean, the indentation, yeah? Is what
Yeah. I mean, if you got a place, I mean, imagine that this is on the tube. You have something like that. Okay. It's just a piece of the tube. Okay. The tube is here. Okay, this piece of surface here is a saddle, negative curvature.
Yes.
What the tube is? No, it's better, I think, but it's right. Okay.
Similar to zero. The idea was in this place to organize some local dynamo, what I understand from this.
This is within the tube.
Yes. Oh,
Yeah, but does this not mean that you are constraining the motion to be along the saddle?
Yeah.
but what I know,
You imagine the
it was studied
flow
many
is.
years ago, if you've got this type of motion in solar chromospheric corona, you produce Riemann and something.
Right.
You mean solar flare?
Flare.
Yeah.
Connection.
Yes.
So this maybe some additional feature of this phenomenon to know.
I mean, you could then have a two-dimensional dynamo, right?
Yeah, red dynamo.
Is that what you said?
Yeah, but with negative current, this is an interesting point he mentioned, because we know from Cauchy's theory, in general they say, okay, two-dimensional dynamos does not exist. But they do exist, it's proven that if the only case you can have fast dynamos in two dimensions is that exactly they have negative current. So actually this is, this result is an application of previous results of mathematicians, but for a very simple solar dynamo model.
But we are not so much concerned about fast or slow. I mean, even slow is already amazing if it works, right?
Yes, but you see the point is that this is Vichyc's anti-fast dynamo theorem. So if you have a negative current, this is in two dimensions. This is the only way that you have fast dynamo.
But what doesn't matter at this point so much?
You mean the velocity of the dynamo? Okay.
Garcia, you know what might be main problem of
Mm.
this discussion? Suppose you've got special place with negative curvature. And suppose you've got dynamo. What happened then, but somehow it should be arrived to positive curvature, another
Alright, what, sorry?
positive curvature, another
okay.
part of your magnetic tube. What happens with you more? Because you produce some local analysis.
Yeah.
What the global features may be not so obvious in this situation. And of course it depends what the weight of this negative curvature plays. If it's very small, it doesn't impair the dynamo in general.
Okay. Yes, I'm glad that somebody, I think as you mentioned, the coronal mass ejections, because here I compute for that case, for the solar data, for CME, I compute the frequency surprisingly big. I mean, it's order of 100 gigahertz. So, but this is frequency that appears in tokamaks in laboratory. So this seems to be a nice result that came out of a geometrical model.
My question is now,
Negative curvature.
suppose you've got beautiful. In some special place you've got negative curvature, and
Sure.
another place positive. So just in this special place you've got, according to result, dynamo, possibility for dynamo. If it's very small and you cube large, it means that the contribution on this place very small compared with all configuration. It's like, what happens in
Yeah,
reality?
I know what you mean. For example, when you have, for example, the perm dynamo, you have the toroidal configuration. And the torus, the average curvature is zero, right? So you have a piece of the torus where you have positive curvature, and you have another piece where you have
For
negative
example,
curvature.
For example.
Okay, but dynamo action there, as far as I talked to Dimitri and other people from the Russian experiment, dynamo action there is a rule. So maybe.
They had in this situation after effect. It would be another story.
Okay. Yeah. In that, it's kind of general.
Okay.
So that's basically it. So that's
So we have sometimes for some questions.
Yeah, I mean, it's been puzzled. What needs to be done to check this now? I mean, there was a question that was brought up, which is not completely clear whether even me or Nathan understood it correctly. Do you think Nathan understood it correctly?
Yeah, I guess so.
He was asking
You always
what
understand.
happens if you take the full thing into consideration, the pieces with negative curvature and the pieces positive curvature.
Yeah, well,
I mean,
in the average, probably we won't have any dynamo action. In the average.
you will have,
So I agree.
you
So
will have
you get any dynamo action.
any. I mean, dynamo action or non-dynamo?
Non-dynamo. Yes, but it's funny because I was given that example. If you consider the toroidal, okay, in the torus, you have pieces of negative curvature and you have pieces of positive curvature. Okay, and you end up with the dynamo action. So probably in this case, I mean, you have some, I don't know exactly how, but it seems that you have more contribution probably from the negative part of the torus than the positive of the.
But I mean, you're
There is
talking
symmetry.
about the curvature of streamlines, right?
On the surface.
Magnetic lines.
Magnet lies over the surface. They are constrained, as in this case, you constrain to, the turbulence flows to a spherical geometry.
So what, and the velocity does what? So he's saying,
No velocity something.
No, yes, there is velocity, sorry. Yes, there is velocity. Here. Sorry. Yes, wait, yeah, here. This is velocity.
Yeah, but an
There's
equation
the rest of it.
for U lambda. Let us check it. Let us
Okay.
look through equation
Lambda.
Yes,
This one.
Where is contribution of velocity in this formula?
Is here through the frequency. Oh, because you see, this is actually there's a misprint here. This is omega, over k1 because velocity is here. You see, this is curvature, okay? Curvature is in the inverse of the radius. So omega versus the radius velocity. So velocity is either here, sorry.
But plus one, it's something maybe.
Sorry?
You've got additional mistake.
Plus one, yes. Huh?
It's impossible. 1 plus velocity is done to more. Okay, let me discuss that.
Okay.
Some
Yeah,
more
but no, but this is not one. You see, all this term here is divided by k.
First term in this bracket, is this
Yeah.
one? No, first term, first.
Yeah.
One?
There's one.
One.
Yeah.
1 plus velocity, it is impossible. I agree. Meter per second, so something, you should add some velocity, I don't know.
Okay, some more questions? Okay, otherwise, we thank Garcia and all the speaker of today or this morning again.